Hello and welcome to Stocks Down Under. Today we're joined by Mohamed Sabry, the CTO of EMASS, which is actually part of Nanoveu. Good morning, Mohamed.
Good morning, Mark. How are you? Nice talking
Pretty
to you
good.
again.
Absolutely. It's a lot has happened in the last couple of weeks. You had some very good news, twice actually. But maybe to kick things off, tell us a little bit about EMASS for people that don't know the company. What's the technology? What can you use it for, etc.?
Yeah, sure. EMASS is short for Embedded AI System. So what we do, we are a fabless semiconductor company that designs AI at the edge. Now, this sounds a little bit too complex or too technical, so let me try to make it easier for people to understand. So we design computer chips that is mainly used to run AI applications very close to where the sensors are, so where the data is being generated. And that's what we call edge computing. So instead of taking your data and sending it to the cloud or sending it to your mobile phone to do your AI pieces in it, we're building a chip that can run on a battery with very small power and can run the AI very close to where the sensor data is being generated. And that way we're open new frontiers, right, in the AI era or in the Internet of Things realm that we are living in nowadays.
Right. So we'll get to a few application areas for the product, but specifically, ECS-DoT, which is the name, sort of, I guess, well, not generic, but sort of the name you're using for now.
Yes.
And then I guess you can sort of specify later on when you've got iterations of that. But how does it compare to other solutions out there in the market? I saw in your webinar the other day, you had a number of competitors in there. And in the research that we wrote a little while ago about EMASS, we talked about that as well. But maybe at a high level, sort of what makes your product stand out from what's out there in the market at the moment?
Yes. Yes. So, our chip, called the X-Dot, right? So ECS, I tried if you combine it together, called X, right? So it's a kind of a play on the X-Men, and it's short for embedded computing systems. So just, little bit of play on words there, but it's something that can run AI on extremely low power. So our game, right, has been from day one, try to improve the energy efficiency. So it will be a no-brainer if I tell anyone, hey, our chips consume the least amount of energy when running the AI applications compared to any chip outside there. So that's something that you will find. And when we talk about low power here, we talk about 1, 2 milliwatts, in some cases even sub milliwatt, right? Just to give a comparison, right? Mobile phones in general consume somewhere on the range between 5 to 15 watts. So your smartwatches, right, would be around 2 to 5 watts or 1 to 2 watts. So this is even 1,000 times smaller, right? So we're talking things that could either on a battery last for days, weeks, or months, right? Or can even require a significantly smaller battery, or even can work on capacitors and energy harvesting devices to supply enough juice for the system to run its AI applications. So we are, as of today, we can be 20 times or even more energy efficient, which means that we can run the application as fast as the fastest chip available out there, but at the same time, simultaneously consume 20 times or even more energy, right, than what's other chips are doing. So that's one thing that will make us stand out in terms of technicality. Another thing that also will do us is the availability that we can interface with multiple sensors at the same time. So we get data from multiple sensors because as you put things in one system, let's say we want to put a chip in our VR specs, right? So there are a lot of things to detect the tilting of the head, to detect the orientation of your eyes. So you need all of these sensors there to be get together. You can run the AI. So our chip allows you what we call sensor fusion. It gets all the data together, then you can run the AI piece on it, and then it will allow you to take an informed decision based on that. So that's another thing that we have there. And also, one thing is that our chip with the ecosystem is very, very compatible with existing software solutions for AI. So any user who wants to use the chip, the engineers who will be developing it, should not spend a lot of time ramping up their knowledge to use our chip or replacing existing solutions with our chip. So it will make the time for adoption very quickly, which should be essential, right, for the success of any kind of chip company, right? Especially if you don't need to educate the end user that he has to redesign or reuse a completely new ecosystem to run applications on it.
All right. And so when you start to think about it, about especially the energy consumption, which is extremely low, as you said, there must be millions of applications, so to speak. But specifically when it comes to real world applications, what do you think are the sweet spots for your technology?
All right. So when we look at, the use, the way that my application, my chip has been designed, right? It is needed. I'm going to be a little bit more technical here. It's needed in cases that you need something that where the environmental data is not too fast. And what I mean not too fast, like I can give you 50 times per second or 100 times per second, right? This is what we call not too fast because in the realm of computing world, we talk about like millions or billions, right, interactions per single second. So hundreds or thousands, that's quite low. And that's mainly all of the environmental sensors where it is from biometric, biosignal data, inertial data, some motor data, right? Some electrical charge data that you can have in that pace. So you take this, you take the decision very quickly, and then you can go to sleep. The chip can go to sleep and then get up again. And by doing something like that, you will find application in the wearables domain, you can find in agricultural domain, you can find even in predictive maintenance, automotive domain, you can find use case even in the drone domain that require a chip that will take data, let's say every 1 millisecond or so, run the AI, and then be ready for the next sample. And ideally, when it's waiting for the next sample, the whole thing is turned off, but it doesn't lose its computing state, right, while being turned off to save power.
Right. Okay. So one area of application would be drones, where you've made an announcement about that. I know you were working on that already, but last week you announced that adding your chip to certain types of drones is extended the flight time by 33%, which is a lot. But can you just explain how significant this is, right? Because people might say, oh, I don't know, 20 minutes extra for a drone, that's not that much. But if you in percentage, it's massive. And I see applications not just in consumer drones, but especially in more, it's a professional type settings where this could be a game changer. So how significant is this? And also, how significant is this for the visibility of the chip and maybe even in other areas?
Yes. So, when we look at when we thought about the use case of the chip in the drone, right, we wanted to do something that has a bigger dent or bigger impact, right, on it than what other AI chips would do. So, it's a no-brainer that you can put the chip in any drone and then start doing object detection and all that. But if you take a chip that has 10 watts versus a chip that has 1 milliwatt, it doesn't solve the main challenge in drones, right? Which basically you have a limited battery that would affect your flight time because all of your energy or the biggest chunk of it goes to your propellers, right? So if you can control the propellers with an AI chip, right, that would allow it to save the energy needed. So this is what the motivation that we have done and the observation we've done. We've started building our own simulation environment, the analysis environment to get that with our chip. We managed to respect the critical delays. We managed to get the AI piece running, map it onto our chip. So we managed to extend the flight time by 33%. Now, as you said, going something from 1 hour to 1 hour, 20 minutes might not seem like a lot, but in fact it is, right? Any extension of the flight time by this amount, right, means one of either the two things. You can either now have this reserve, right, so that the allowing the drones to safely go back to a base station, right, which is unaccounted for doing this. You can make it go for longer distances, right, like extra 20 minutes if you're running at 100, if you're flying at 60 kilometers per hour, right, that's going to be another extra 20 kilometers. So that's quite significant, right? That's quite a bigger distance to go. It will also help you to make sure that when you're navigating, you have some safe backup energy, right? In case for any kind of critical failure, you can just turn on the eyepiece and then this extra energy is there, allow the drone to go back safely. But on the flip side of coin, this means that I can reduce my battery by 33%. right? And by raising my battery for 33% means that the drone is now lighter, right? It can have a bigger payload, and that's good for drones that perform some sort of delivery. So instead of like 1 kg, right, now I can do 1.5 kg, right, of payload. Instead of 10 kg, 15 kgs of payload, right, on the same drone for the same flight time. Just now it's using a lighter battery, and that weight I'm using it to enhance my payload capacity. So this kind of thing, right, would help a lot in making drones, right, like outreach more or can have wider use cases, right, and having, I mean, more variety in terms of applications. The same concept could be taken, right, and can be placed in smart grids for electricity. It can be placed in automotive for predictive maintenance, right, helping things in the state of charge, helping things in bigger motors, right? The same, you can like work with that there, but those would require different challenges with different analysis. So we can try to take it and put it in this case. Ideally, is that from a very, very general thing, the use of AI to control mechanical components to save the energy it's being used, right, could be something new that's like edge AI combined with advanced control systems would unlock significantly in the next 5, 6 years. And I'm starting to see companies that are using the same thing, but in other applications in terms of energy creation, right, in like wind turbines and whatnot.
Right. Okay. So if we look at what you're doing now with the drone specifically, not looking at say 5 years, but just looking at what you announced in the recently. Obviously, you can't name any names of these OEMs that you're working with. But if you look at where you are now versus where you want to be in terms of commercialization, is there any way, any sort of timeline you can indicate to, as in how long that might take to get to commercial status?
So, I mean, if you ask me what's my goal, right? I'm hoping to have a drone, right, being actually in test with our chip, right, towards the end of this year. So, an actual flying drone, right, with one of those partner companies using our chip mounted on it with the routine there by the end of this year. So, that would have actual drones, right? When we roll out our chip in production, which should be in the second quarter of 2026, should be by the third quarter having drones already with our chip model that can fly extra time, hoping that we can improve our algorithm to push this 33% even higher than that. So that's our main goal, right? Because and that aligns with our strategy in commercialization because right now we are working towards improving the chip, right? Getting a smaller chip, moving for larger scale, building even more advanced evaluation board and modular development kits so that can even accelerate that adoption, not just in the drone market, but in fields in predictive maintenance, wearables, and other applications as well, such as like asset tracking.
Right. Okay. So yeah, there's a lot to look forward to then in terms of development, I guess. Just this week, you actually announced you're scaling down from 22 nanometers to 16 nanometers.
Yes.
Of course, yeah, for people that are not familiar with semiconductors, it's a big step. It's a mature technology. That's also important to mention. But specifically for you guys, how significant is this, and why do you want to get this chip smaller and smaller?
Right. So, I mean, to start with, I mean, the numbers, right, might sound okay. I mean, like 2216 is a smaller number, but in the era or the field of semiconductors, a smaller number means better, right? Stemmed with energy or technology node or the chip area. So, we do it 22 to 16, meaning that you're going to go with a smaller transistor dimensions, meaning two things or three things happening at the same time. One, you will be able to have more transistors, which means that a bigger, more functionality in the same chip area, or you can have a smaller chip for the same functionality. Two, you can run things a little bit faster because with the smaller transistors, you can afford to switch things on and off much faster than it was before. And you can do this simultaneously while consuming lower power. So our energy budget will be even reduced. But we're doing this to make the chip extremely small to fit cases like in the ring, right, in the next generation of AR, VR systems, where footprint becomes extremely critical. You don't want to wear a specs where you have a very wide arm over here. Ideally, you want something still with the existing arms like that so that you don't have to like make people, right, accept new kinds of design. You want them to use the current specs design or glasses design, but it's now mounted or AI enabled. And that's what makes some of the current products could be more than successful or less on the successful side. So that's very important for us to be able to put the chip into newer use cases that requires even more strict footprint on the chip itself. It will even push the energy consumption right into newer frontiers by having a lower power consumption, and we can actually afford to have more pieces of AI that paves the way towards the generative AI running in such a very small scale. So we're looking to include components that talks about object detection. We're looking about that something called vision transformer. We'll be able to try to include it in this kind of chip, thanks to the availability of this couple of or like new real estate on the silicon die that we can add new modules on it.
Right. Okay. And so when we switch gear a little bit towards your development roadmap, can you talk a little bit about that? What's in the say the next two years or so in terms of development? What's in the pipeline? But also, how much of that is being driven by the OEMs that you're working with now, or other potential customers? How much influence do they have in your development roadmap?
Right. So the main thing, right, given that we're by initially we're on fabless semiconductor, so we'll always have in a timeline a new chip or a new design that will always be out there, right? But it's not just designing the chip, right? We have to make it scale up to be commercial, which means that we need to go for large scale production. So in the next 12 months, what we expect we will have at least one, right, full production line, right, or full production run, right, with our chips. And that's expected within the Q1/Q2 2026. We should have these chips. And we'll talk about at least 50,000, 100,000 chips will be generated or be created, based on some of the designs that we have. So that's on that the first 12 months. We will also work on it to enhancing our software ecosystem to make it very, very easy to be adopted by end users, right? And have also a lot of built-in functionality support to very quickly increase your AI capability or even develop new applications from scratch in case the user doesn't have that as well. Now, switching things up, right? As we work with some of the partners, we found out that some actually were interested in putting the chip strict into what we call sensor boards or development kits, right? So we are redesigning our development kit, right? Making it into a very small one, form factor, something on like that size, right? And then we'll be able to put or take off, right, and plug and play different kind of sensors. So it's the same module. Now, the module for wearables, the module for drones, the module for automotive, right? Module for predictive maintenance. All you need to do is just like take some stuff up, put some things again, kind of like Lego, right? And that's actually concept was very appealing to the OEM partners that we are collaborating with to be able to create that. And that will also accelerate, right, our entry to new uncharted market segments that we are not aware of. For example, in asset tracking, right? This is where they need a lot of intelligence in it right nowadays, beyond simply a GPS to know where the things are. They want to know if the goods are good or turning bad, right? And how far off they have before expiry. So all of these things, right, requires some processing. So they told us, okay, if we can develop this kind of systems, right, together, they will help us even in reaching out to these kind of segments that they are well connected to, right, and it will be enabled by our new technologies.
All right. Okay. So last question, Mohammed. If we translate all that into commercial milestones, say the next 12 or probably a bit longer, 24 months, what should investors be looking out for?
So investors should be looking at, the first 6 months from now until end of the year, a lot of proof of concept, right, will be created in partnership with these kind of tier one partners. Now, when we do proof of concepts with them, meaning that they are already very serious, right, in taking this and buying it from us, but we're doing this kind of called the design-in phase. Now, so by end of this month, you will see, by end of this year, we'll have a new chip, adoption of new drones, we'll have the new modules. the next year, right, which is going to be in line with the design cycle of, some of the wearable companies, right? We going to be landing some deals to design in some wearables, right, with them. We are now in the midst of the conversations, right? So hopefully we can get in 2026, start working with them. So by Q2, we're hoping we have our first purchase order, or even end of Q1, the first purchase order already signed with them, so that we can supply the chip and the technical support. But in the meantime, we're hoping we can get some sort of engineering support, right, contracts, right, with some of these partners as well. So we're
Right.
looking at a lot of news in terms of technical development the next 6 months, some commercial, but the biggest commercials will happen in 2026, and hoping for, look, really big customer, orders that will be coming on our way.
Right. Okay. Well, that was my big takeaway from the webinar this week as well. Commercialization seems to be closer than many people thought, actually. So I think that's very good news. Mohammed, thank you very much for your time.
Oh, my pleasure, Mark. Always, yeah.